once again, good afternoon or good morning if you're further out in the West. Welcome to this Water Institute Water Talk at the University of Waterloo. My name is Roy Brouwer, and I'm the Executive Director of the Water Institute. Before we start with the Water Talk, as always, I would like to acknowledge that I'm participating here today from traditional territories of the first people. I participate today from land that was part of the traditional territory of the neutral Anishinaabe and Haudenosaunee people. And here you see a map of the land. We're located on land granted to the Six Nations that includes 6 miles on each side of the Grand River as part of the 1784 Haldimand Treaty, totaling almost 400,000 hectares of land. These days, the Six Nations Reserve is located on approximately 19,000 hectares. I encourage you all to take a moment to recognize the traditional land where you are. University of Waterloo and its centers and institutes like the Water Institute are committed to raise awareness and committed to contribute to Canada's Truth and Reconciliation Commission's calls for actions. Before I introduce the speaker for today, a few housekeeping items. As always, please include your questions in the Q&A box, not in the chat box. And then at the end of the talk, my colleague Nancy Goucher and myself will get to these questions. If you have any technical issues, you can use the chat box, and then our producer, Julie Grant, will try to help you with that. The webinar will be recorded and posted to the Water Institute's YouTube channel afterwards. So it's my pleasure now to introduce the speaker for today, Dr. David Sedlak. Dr. Sedlak is the Plato Malozemoff Professor in the Department of Civil and Environmental Engineering at the University of California at Berkeley. He's the director of the Berkeley Water Center and deputy director of the National Science Foundation Engineering Research Center for Reinventing the Nation's Urban Water Infrastructure. Professor Sedlak is a member of the National Academy of Engineering and recipient of numerous awards, including the Paul Bush Award for Innovation in Applied Water Quality Research and the Clark Prize for Excellence in Water Research. Dr. Sedlak is the author of Water 4.0, the past, present, and future of the world's most vital resource. After receiving a PhD from the University of Wisconsin-Madison, Professor Sedlak spent 2 years as a postdoc in Switzerland at the Swiss Federal Institute for Aquatic Science and Technology, also known as EVAC, before joining the faculty at UC Berkeley in 1994. Professor Sedlak's research focuses on the fate of chemical contaminants with the long-term goal of developing cost-effective, safe, and sustainable systems to manage water resources. And the title of his talk today is The Next Water Revolutions. Professor Sedlak, we're very happy to have you here with us today. I'm happy to open the floor to you. I will stop sharing and so that you can share your screen with us.
Great. Okay, give me a moment to share my screen. And we'll be off and ready to go. All right. Well, good morning, good afternoon, everyone, I guess, and welcome to the Water Talks. I'm very happy to be here today. I want to thank Roy Brouwer and Kevin Boehner for inviting me to this talk. I wish I could be there with you in person, but that day will come pretty soon. So every day I get up early and I think about revolutions. I think about water revolutions and the way they're going to help us change the system that we have for delivering, managing, treating, and disposing of water. And I didn't set out to do that. It kind of happened to me on my own because I was busy trying to explain to people some of the research that we were doing, some of the changes that we were seeing in the Western United States to the way that our cities were providing water. And to explain this to people, I ended up writing this book called Water 4.0. And the thing that I learned as soon as I sat down to write this book, that change comes to water systems all at once. And those changes we often refer to as revolutions. And so I was talking about Water 4.0 because I had learned as I studied water systems about the first revolution in water, where we moved to centralized supplies, as indicated here by this image of a Roman aqueduct. But we also use this approach of sourcing our water from long distances and transporting it into our cities to make it possible for millions of people to live in places where there might not otherwise be a sustainable source of water. And once this idea of imported water became commonplace, you wouldn't imagine building a city without it. So it really was a revolution. The second revolution in water systems happened when so many people started to live in such a small place. So as the world urbanized, the wastewater from upstream cities started to contaminate the drinking water supply of downstream cities. And so rather than continuing to source our water from pristine locations, which we just ran out of, we developed drinking water treatment plants. So at the turn of the 20th century, engineers developed chlorination and sand filtration and essentially ended the scourge of waterborne diseases in wealthy countries around the world. And afterwards, you wouldn't imagine building a water system without a drinking water treatment plant. The third revolution in water was the development of wastewater treatment plants. And of course, wastewater treatment plants have been with us for over 100 years. The real innovation came when people finally got frustrated with dying fish and horrible odors in our cities and rivers catching on fire. And they responded by investing in the infrastructure that became modern wastewater treatment plants. And once those investments were made and people saw how much better surface waters could be running through cities, it was a revolution. And you wouldn't think in a wealthy country of ever building a water system without it attaching a wastewater treatment plant. And so that was what led me to Water 4.0, this idea that we're undergoing a fourth revolution, a revolution that's driven by this idea of introducing circularity into urban water systems, the idea of recycling wastewater, of capturing stormwater that falls within the city and reusing it or using it in some way. And that was kind of the story I told and the thing that I think about in my research within the Renew It Research Center. And this figure here is one that we often use to help us orient ourselves. But one of the great things about writing a book for general audiences is it forces you to confront questions that you wouldn't otherwise think about. So in my own research, when I wrote the book in 2009 and when it came out in 2014, I was very focused on wealthy countries where there was water scarcity. But when I started to talk to people and give interviews and travel to talk about Water 4.0, I was asked questions that I couldn't answer. And learning from people who are dealing with their own types of water crises, I've come to think of the water crises as multiple in nature. And these are the 6 water crises that I think are very important around the world and where we can think about placing our research and look for synergies among them as ways to solve problems in the future. So I've given a number of talks on this topic of the 6 water crises over the past year or two. You could probably find them online. I'm not going to go into detail about the 6 crises today because I want to talk with you about the revolutions. But you can see here that 3 of those water crises are water supply crises. I work on the one in the upper left-hand corner, water for the wealthy. So you see a seawater desalination plant north of San Diego in this image. And many of you are familiar with the challenge of providing water for people who lack access or poor people. That is, under SDG 6, we often talk about the idea of reducing the number of people who lack access to water. But there's this crisis in the middle, water for the many, which is probably more important in some ways than either of those other 2, because the majority of people on Earth live in middle-income countries and already have access to water, but that water is either insecure or too expensive or contaminated in some way. The bottom 3 crises, water for health, the first of them, water for health, it transcends issues of wealth. It's the contaminants that we deal with. So maybe this is an image of someone pumping arsenic contaminated groundwater out of a tube well, but many people in wealthy countries struggle with arsenic in their drinking water, and people all around the world have to address issues like PFAS or other contaminants in their water supply. Water for food, obviously a huge issue. The majority of water that's used consumptively is used for food production. And if you don't have water, you don't have food. And so it becomes a huge challenge when we think about the growth that we expect in coming years. And then finally, water for ecosystems, as indicated here by the picture of the Aral Sea drying up, is also one of great interest to many of us here today. So these are the 6 water crises. And my premise of today's talk and my premise that I've been thinking about for the last few years is that we're at a point where all of these crises are seemingly getting much worse. And we're going to need new solutions that go beyond the status quo, beyond the established solutions that we've been using for the last few decades. And there are two main drivers for this, in my opinion. The first of which is global growth and development. So this figure shows you 12 plots from something that we refer to as the Great Acceleration. And so it's the idea that during the Anthropocene, the period starting at around 1950, not only has population shot up, but GDP in terms of wealth has shot up, people have moved to cities, and with this shift, we've seen changes in dietary habits and a need to produce more food. And so between producing more food and supplying more water to people who live in cities, we've had to create a lot of water infrastructure, and we run into the 6 crises that I showed on the previous slide. But the second reason that we're moving towards greater frequency of water crises is climate change. So this is Lake Shasta here in California. You can see this is 5 years ago when it was empty, but I think it was about this empty last year, and it picked up a little water this year when it rained. But you know, if you've been following the news, both the aridification of the Western United States, the increasing droughts in places like the Mediterranean and Australia and Southern Africa really are challenging our ability to deliver water. And so it's driving a lot of crises. Now, in normal times, the way in which we deal with water crises, and water crises have not just started the last few years, even though it may seem that way, water crises always happen. But normally the way we deal with water crises is through water evolution. That is, over periods of many decades or generations, we see our water systems undergo a process of evolution. We see new innovations that make systems perform better, and when they stack up on top of each other, this makes a big difference. They tend to use existing technologies, and those technologies slowly get better and better. And more importantly, water evolution doesn't really change the institutions responsible for managing water. So let me give you 2 quick examples of some of the most powerful types of water evolution that we've seen over the last few decades. Here's one. It's agricultural irrigation in the Western United States. So you can see from the orange and the brownish red line here that over a period from 1984 to 2013 in the Western United States, we switched from gravity irrigation, or essentially flood irrigation, to pressure irrigation. And pressure irrigation are sprinklers that use less water. And that switch, which happened over that 30-year period, was accompanied by great increases in the amount of food that was grown, but no real change in the total amount of water used. And this is a common phenomena that resource economists see, Jevons paradox, that as we introduce new technologies, we maybe increase the yields or we increase productivity, but we don't change the total amount that's used. So it makes it very good for long-term adaptation of a system. It makes people wealthier, but it's not very effective in response to an immediate crisis. And the same phenomena can be seen in urban water systems. So this is a figure from the city of Los Angeles. And what you can see here is that over a period from the early 1970s to the mid 2010s, the total amount of water used by the city of Los Angeles remained approximately constant as conservation measures, low flow toilets and appliances, led to a decrease in per capita water use. So it went from 190 gallons per person per day in 1970 down to 137 gallons per person per day. It could probably drop a little bit more, but you have to remember in the Western United States, we can't have lawns and gardens and ameliorate the urban heat island effect without using some water outdoors. So even Los Angeles, which you may have an idea, is full of swimming pools, is becoming a lot more efficient in its water use. But this is not something you use in response to crisis. This is something you bring in over a long-term period, and it has to do with a lot of complex issues that Professor Brower could probably talk to you about, revenues and the like for cities. I'm more interested today in water revolutions. A water revolution, and I think you can think about these on a continuum, because obviously we don't throw away what preceded a system, but they happen more quickly. And they're generally done in response to a crisis, like the 4 water revolutions I introduced this talk with, but they require some sort of new approach. Maybe it's a new type of technology, maybe it's a management innovation, maybe it's a change in water rights. And when they happen, they tend to permanently alter the nature of water institutions. And so in today's talk, I want to give you an example of 5 water revolutions. And they're things that I think will change water systems and be useful in response to all 6 of the crises. Maybe there's a little bias towards wealthy countries because that's where spending happens and that's where a lot of these innovations start. But I'm sure that they're going to spread to other places over time. I'm currently writing the follow-up of Water 4.0, so I'm going into this in some amount of detail in my writings, and I'm also making these 5 revolutions somewhat central to my own research. And so because I'm trying to cover so much in such a short time, I won't go into great technical detail. I'll put references to papers that we and others have published that you can refer to if you want to learn more. And you can always write to me after the webinar, Sedlak at berkeley.edu. I'd be happy to talk to any of you about this. So let me go with the 5 revolutions. Please humor me here as we talk about them. So my first revolution, I'm going to call Still Suit for a City. Now, I've been a big fan of Dune since I was a teenager. It didn't take a new movie to make me excited about the ideas in Dune. And one of the things about this classic 1960s era science fiction book that really struck me was the idea of a still suit. The still suit was something that the people of Arrakis wore when they went down to the surface of the planet, and it conserved their water. So all the water, not only that came out of their bodies, but that they breathed out or that they sweated in the hot sun, was collected by the still suit so they could consume it again. And the idea that water could be recycled over and over again as a way of living in a place that's very dry had a lot of appeal to me. And a few years ago, when an alumnus of Berkeley challenged us to make little short 2-minute talks about innovation going on in our research, I chose Still Suit for a City as the title of my talk, and I want to stick with it because I want to show you how cities are and will in the future start to behave a lot more like still suits. One of the ways in which cities will start to behave like still suits in the future is through the practice of potable water reuse. And this figure shows you the places around the world that are leaders in potable water reuse. By potable water reuse, I mean we take the effluent from a sewage treatment plant, we subject it to additional treatment, and we reintroduce it into the drinking water supply. And I made each of the dots here equivalent to about 100 million liters per day of capacity. And what you can see looking at this figure are several things. First of all, the leaders in potable water reuse around the world are in Singapore, where it's part of the national security program, and California. What you can also see is that sometimes we in the Bear Republic think of ourselves as different from the rest of the United States. That sometimes is true when it comes to water reuse, not just to our politics. And so I think we're well positioned here from what we've done over the last 40 years to understand where the trajectory is going with respect to potable water reuse, closing the loop and making urban water systems more circular. I think also it will eventually spread just beyond these early adopters. So the first place we can look is to the OC, and that's our diminutive name here in California for the area south of Los Angeles, referred to as Orange County. So when we talk about the OC, we often think about Orange County, and what happens in Orange County is essentially all of the municipal wastewater is being recycled and put back into the water supply. So there is no more sewage effluent in Orange County. The only thing that's going out to the ocean is the RO concentrate left over after the water goes through reverse osmosis. And I list a couple of papers here. One, for those of you interested in water quality, that was published in Accounts of Chemical Research in 2019, showing the treatment technologies and the way they protect us from waterborne pathogens and chemical contaminants. And the other, a little bit of an older paper, was our effort to understand how these systems underwent the process of legitimization and how the public came to accept and embrace investments in potable water reuse. And so if you think that this is something that's going to happen far into the future, come to Orange County, you'll see that the future's already arrived there. A second part of Still Suit for a City that's taking place is the idea that stormwater that falls within a city can and should be recharged directly into the drinking water aquifer. And for many years, cities tried to avoid this. We tried to move the rainwater that fell in our cities out as quickly as possible to avoid urban flooding and to avoid the possibility of contamination. But now Southern California, in particular the area around Los Angeles, is installing regional recharge facilities where they're capturing stormwater runoff and increasingly dry wells to get that water into the ground. And I was very intrigued when I first heard about this and got involved with some research with the city of Los Angeles on developing passive small-scale treatment systems, because the stormwater coming out of the streets is not safe to drink without some sort of treatment. And most groundwater systems, people access that water without any additional treatment. So to avoid introducing contaminants into aquifers, we've been developing small-scale distributed stormwater treatment systems. And you can see a couple of papers here, one in which we developed an advanced oxidation process for stormwater that could operate without being connected to the centralized water system, and the other a geomedia material. But this is kind of a start of a movement that we've been pursuing within the Renew It Research Center in terms of cleaning up stormwater before recharging it into aquifers. And so when you put these two things together, it becomes clear that we can create a still suit for a city, and that still suit is a little bit leaky, because we're not going to abandon our imported sources. Even if the climate changes and we have less water available, we'll still be bringing some fresh water into our cities. And we're not gonna be able to capture and recycle all of the water, because we're gonna lose some water through evapotranspiration, or we won't capture all of the runoff in the city, or some of that groundwater will be discharged and lost to the ocean and lost to the regional aquifer. But I think that when you consider a city as being able to partially close this loop, it really changes the equation, because your reliance on imported water systems is greatly diminished. My second revolution that I've been thinking a lot about lately is something that we refer to as net zero water. That is this idea that you can build buildings and industrial parks and housing complexes that don't draw any water from the system. They collect all the water they need through rooftop rainwater collection systems. They recycle the water within the building, and they discharge it in some way or another. And this idea of net zero water buildings starts to look really interesting when you consider the way in which technology development and adoption occurs. And I wrote this paper in 2020 with my colleague Cornel Rabai at Ghent University in Belgium, thinking about the draw or the attraction of so-called personalized water systems, the concept that not only would you be able to save money perhaps by cutting your ties to the centralized water system, but you might actually create a user experience that you value more than the existing water system that you have. You might be able to make water, for example, for your washing machine that's already softened so the detergents work better. Or you might be able to get the ion balance in your tap water when you're cooking or when you're drinking that is more favorable to you. And these kinds of like high-end innovations would lead to investments in systems, and then those investments would scale, undergo the so-called learning curve, and the cost of producing them would decrease, much like rooftop solar, much like cell phone technology developed first in some kind of niche, wealthy country purposes, and then eventually dropped in price and scaled and had a much bigger impact. And this idea that we talked about in the paper was really interesting to us. And I just wanted to kind of give you a little bit of a flavor of some of the things that we're thinking about when we consider the idea of spreading this technology further. It's the idea of where you're located, and the places that might adopt this technology first are the places that have greater water scarcity, because people are grappling with this question of how to provide water. So when we ran simulations for Belgium, our rainwater tank never emptied because it's raining almost constantly over the entire year in Northern Europe. But when we ran simulations of what would happen in California, we realized that every year at the end of the dry season, we'd have to have a tanker truck come and refill the rainwater tank. And that was very inefficient. So you'd have to think about it not being very practical in a Mediterranean climate like Southern California. We've also started looking with a larger team, including some researchers at UC Irvine and the University of Girona at the idea of going from single family homes to multifamily dwellings all the way up to large apartment buildings. And we've kind of done a techno-economic analysis, and we see that these things start to make economic sense when you consider the tariffs that are charged for water. So when you start thinking about this the same way that people think about rooftop solar, if you reach a certain price point, it actually starts to pay for itself without any subsidies. But what really makes these things interesting to me and really convinces me that this has the potential to scale further is the concept of combining this net zero water buildings with extreme water conservation. And I think the best example of this is a group called the 50 Liter Home Coalition. It's a group, you can see the participants here on the right-hand side of the screen, that came together a few years ago with the objective of dropping per capita water use from something like, I don't know, about 100 liters per day or 150 liters today, which is kind of typical of most cities around the world, down to 50 liters per day by using things like recirculating showers and washing machines that only need a few liters of water to wash your clothes. And when you look at these and pull it together, it really starts to change the equation, because then the sizes of the storage tanks and treatment systems you need in the net zero home start to shrink, and they become even more economically competitive. So that's my second revolution. The third water revolution I'll refer to as a better salt machine, and it'll become evident to you what I mean by a salt machine. But for now, I'll just say that this is a picture of a so-called concentrator, which is used to take the brine produced by brackish water desalination and recover water, eventually sending it to a crystallizer or an evaporation pond where you can create salt and then dispose of that salt in some matter or another. And the reason that this is so important is that there is a huge reservoir of water, or a huge resource of water, that currently goes untapped in many parts of the world, and that's brackish groundwater. So to give you an example of the power of brackish water desalination, I'll give you Florida as an example. And what's really interesting about Florida is that Florida is probably the world leader in brackish water desalination. For the last 30 years ago or so, the growth in the southern half of Florida has been made possible mainly by desalination of the upper Floridan aquifer, which is a brackish aquifer in that part of the state. And this brackish water desalination produces water that's a lot cheaper than desalinating seawater. And as a result, they've built up a very large capacity in a very short time. What's also interesting is that brackish groundwater desalination stops when you get about midway through Florida. They built the seawater desalination plant in Tampa, but it's not used very much because there's nowhere to put the concentrate. So what made brackish groundwater desalination feasible in southern Florida was the ability to do deep well injection into a limestone formation known as the boulders, where there's just incredible porosity, and you could actually use gravity, not even injecting, to get the RO concentrate disposed of. And that kind of brings me to this question of how we deal with brine when it's at the surface of the land. So right now, we don't really have a lot of concentrators and evaporators because they're very energy intensive and very expensive. But we do have experience managing brines from agriculture and from power plants. And our experiences of managing brines from power plants and agriculture are really bad. So any of you who've been around long enough might remember the Kesterson Reservoir in Central California, or if you've ever been to Southern California and seen the Salton Sea with its fish kills and all other kinds of horrible things happening, know that when we take agricultural runoff rich in salts and send it somewhere to evaporate, we can create ecological catastrophes. And likewise, the Palo Verde generating station in Arizona is a power plant that uses recirculating cooling and then sends the brine to evaporation ponds. And those evaporation ponds are a bit of a management headache for the utility because of the expense of operating them and the challenge of dealing with them. And so I see a revolution on the way if we can solve the problem of creating low cost brine concentration and crystallization processes. And so this wonderful article here by Tong and Elimelech that came out in 2016 tells you something about some of the technical challenges and some of the proposed solutions. My personal view is that that's more of an evolution, because we'll see over time a gradual decrease in cost, but it will still be quite costly and quite energy intensive to use these approaches. What I think may be one of the keys to the revolution is returning to this idea of evaporation ponds, but making them much more efficient. And so this paper that I was part of in 2021 with my colleague Bausha Mi and her graduate student Casey Finnerty looks at developing what we refer to as a graphene oxide stalk, which is essentially just a piece of paper coated with graphene oxide that wicks up brine and evaporates it. And the evaporation rates that we can achieve in a system like this can be 10 times or more faster than what we would get out of just a plain old pond. And so as a result, you can have an evaporation pond in a much smaller footprint, and you can also seal the pond off from access to aquatic organisms that might get into trouble when they interacted with it. And so if we could drop the cost, then that goes a long way to allowing people to access brackish groundwater. It also maybe provides a basis for treating salty agricultural drainage water and water from power plants. But at the end of the day, we're still going to have to solve one other problem, and that's the problem of what to do with the mountains and mountains of salt we'll produce. And I think that's also another huge challenge that I hope the research community can arise to. Perhaps it will involve valorization of these salts, maybe extraction of valuable elements. Maybe we could get the lithium out, for example, or get the phosphate out, or perhaps we can produce feedstocks for important commodity chemicals like sulfuric acid and caustic. And I think that's a real challenge for our community to think about in the future. Okay, 2 more revolutions. I hope you all have stamina here. I know I can talk a little fast sometimes, but I'm really passionate about it, so it gets me going. The 4th revolution I'll refer to as another set of kidneys. And what you can see here is an aerial photo of the Prado wetlands in Southern California. It's a place that was developed to treat an entire river. So there was an effluent dominated river called the Santa Ana River. It had nitrate levels that were too high for the drinking water supply. So it got routed through these wetlands, and the process of denitrification in the wetlands allowed the Orange County Water District to avoid the expense of building a surface water treatment plant for removing the nitrate. So I've been intrigued by nature-based treatment systems because they have this potential of being able to treat large amounts of water for a relatively low cost, and have been involved in research on this topic for a number of years. Here's an example of a new kind of treatment plant that we built in that Prado wetlands that we call an open water unit process wetland, and we published a series of papers on them, but this one is the one about the performance of the large pilot scale system. Essentially, if we start treating wetland systems more like the way environmental engineers think about things, thinking about the hydraulics of the system and their performance and the mechanisms through which contaminants are removed, we can make them perform a lot better. And that's something that I think has been a theme through this research. And we've been studying it for a number of years. And recently we realized that these managed natural systems, or these constructed wetland systems, could also be useful for what's turning out to be one of the biggest challenges for some of the other revolutions, and that's treatment of the brines produced by reverse osmosis, and in particular, the reverse osmosis brines from potable water recycling plants. And so we wrote this article, a review paper on this challenge for the first edition of this new ACS open access journal called ACS Environmental Gold, and it describes this situation a little bit. We've also published a few papers on it, so this is kind of a miniature version of that open water wetland where we've been studying the potential use of it for treatment of RO concentrate produced by a potable water recycling system. And we've seen that we can remove nitrate and trace organic contaminants quite well in these systems, and they're relatively cost effective to build. And increasingly, we're seeing these nature-based treatment systems also being very attractive for adoption because of the multiple benefits that they can provide. So this is the so-called horizontal levee or living levee system that we've been working with close to Berkeley. It's a system that was designed not only to improve water quality, but to protect communities from sea level rise by serving as a buffer between existing storm control structures and the bay, and also providing new natural habitat. And the idea behind it is we grow native plants on a sloped surface adjacent to a constructed concrete levee. And as the water passes through the subsurface, microbial community living on sand and gravel breaks down contaminants, absorbs metals, and improves water quality. And when we build them, they're actually quite attractive and quite popular with the public. So this is a picture of our experimental facility, and it's full of natural plants that are native to the area, not nasty old cattails or something like that. And so we think that these have a lot of potential, and we're probably going to build one of these to treat a large potable water recycling facility in the Bay Area in the coming years. The last of my revolutions is not a technology revolution at all, but it's a revolution in the way we think about who's involved in making decisions about water systems. And I'm still kind of in the initial stages of thinking this through, so I appreciate all of your contributions. But the way I think about it is that we need to find a way to bring 3 more seats to the table in the decision-making process and make sure that the 3 groups represented in these seats have their say, but at the same time make sure that having more people involved in making decisions doesn't prevent us from responding to crises. Because I think one of the hardest things about crises is that all of our attempts to engage with the community and take everyone into account often fly out the door at time of crisis. So this requires some work in advance to make sure that we have the ideas, and then when the crises hit, we deal with them. So the first group, and the most obvious group to have a seat at the table, are those people who are underserved. And whether that's in wealthy countries and the awakening that we're having here in North America to all of the people who have historically received poor water service for reasons of environmental racism or the sheer fact that they live in rural communities, it's an important topic, and it's one that we're seeing a lot of investments in. And I think one of the keys to this is getting beyond just talking about the problem and how unfortunate it is and finding solutions. And in California, we passed a so-called human right to water a few years ago. And now we're just in the process of figuring out how to implement and realize the human right to water. And that's something that this organization, OEHA, one of our health agencies, is doing. And I don't have time to go into this. I encourage you to look at the report. But the idea is we look at who is underserved in terms of the quality of the water, the accessibility of the water, and affordability of the water. And we work with those communities to ensure that they reach a certain minimum standard. And I think that idea that there's a human right to water, that to be part of a society, to be part of a civilization, you need helps us understand and reconcile a place for the underserved and to get them at the table making the decisions about what those systems look like. The second group that I think needs to be at the table are the people who have yet to be born. Oftentimes when we talk about climate change, for example, we talk in terms of discount rates and impacts that will affect future generations, but we don't want to deal with now because they're not as important as creating the economic growth needed by the current generations and to make the future more wealthy. But what if we started putting aside resources to enable future generations to deal with the impacts that we've created by the way we've managed the world? I think that that's something that we're going to see more and more discussion of as the world grapples with climate change, but I also think it's one that will be increasingly important in water. I think that things like hiring a minister for future generations is one way to get them a seat at the table. And I encourage you to learn about what people are trying to do in Wales, for example, of actually making sure that there's a person who represents the future. And finally, I think the third seat at the table needs to be filled with someone who represents the environment. And a great example of that are the environmental groups that stand up and speak for the environment. And here in California, I think one of the most inspirational things that I've ever seen is the way in which the Mono Lake Committee managed to get water restored, the water supply restored to Mono Lake to allow it to return to its start to return to its historic elevations. And they did that through the use of a legal framework called the public trust. And the public trust doctrine, which exists in English common law, it may exist in Canadian code, I'm not even sure, provides a basis for taking water rights back when they impact a public good, and in this case, the public good is the environment. So whether it's in Canada, First Nations, or Native Americans, United States, or Aboriginal people elsewhere in the world who end up speaking for the environment, or whether it's environmental groups, I think a seat at the table for groups who understand and see stewardship of nature as important is also key for us to go into the future. So that's kind of more or less the end of my remarks here. I did want to make some acknowledgements before I go. I wanted to indicate some of the people who've been really instrumental in the research we've been doing. And if you read some of these papers, you'll see their contributions throughout. I also wanted to acknowledge some of the organizations. It's impossible to do this kind of work without having partners in the real world. And we've had a number of partners in the real world. And maybe by way of summary, I want to just share some final thoughts, and maybe that'll lead us into our discussion. So my first final thought is that if you're a revolutionary, be prepared for failure, because revolutionaries usually fail at first. So my experience is that as much as we want to change the way water systems operate, it's a process that takes multiple decades, and one has to be persistent, one has to be willing to make experiments, and one has to be willing to keep going after they fail. So that's something that we may not be as used to, but we really need to be quite persistent. The revolutionaries need partners. So, in our own research, we've worked with a number of utilities and governments and environmental groups. And I think that academic researchers have to reach out and find these partnerships, because they're the people who carry the ideas that we have through to change. And we need a theory of change. We need to dedicate ourselves to understanding exactly how large, complex systems like water infrastructure changes over generations. And our research has to answer questions that decision makers make. And then finally, for those of you who are early career researchers looking for something to do, I encourage you to think of yourself as a revolutionary, because if you are, you're never going to be bored. Thank you for your attention. I look forward to questions.
Thank you very much, David, for this very inspiring talk. Very, very interesting. And I can see with the net zero water building that you have been in EWAC in Zurich, where they have a building like that. Very, very impressive. Thank you so much for your talk. We have a number of questions. If anyone has more questions, please use the Q&A box. I'm just going to kick off with one question for myself, if you don't mind, very briefly. So how do we incentivize these revolutions? Is it pure economics, or is there another driver that you can identify that can help us to achieve these revolutions?
Yeah, so I see, Roy, that we can certainly have subsidies to incentivize revolutions, and that's historically the way we've done it. We've had government programs to create subsidies to make technologies that we anticipate will eventually become more effective, or that have a larger triple bottom line effect work. But I think subsidies are just a small part of it. And my own experience is that we need to have more experiments. We need to have safe spaces where people can try things at a larger scale, not just a laboratory or pilot scale, but the scale of a small city or community, to demonstrate that they work. Because one of the things that's endemic of water systems is that water is a conservative field by nature due to the long lifetimes of infrastructure and the low return on investments and the high consequences of failed projects. And so by tying our subsidies or our incentives to demonstration projects, we start to de-risk them. And when we de-risk them, we shorten the amount of time for permitting, we lower the bond ratings, we make them more investable, and we help people like realize what the possibilities are. And so this happens in advance of a crisis. And then when the crisis happens, people are willing to plunk down money on it. And I think we've seen that with seawater desalination and potable water recycling and reforms of water governance, like in the Murray-Darling Basin. These things work best if in the time between crises, we put our efforts into demonstrating the possible at scale.
Thank you very much. I'm going to hand over to Nancy, who's going to address some of the questions in the Q&A box. Nancy?
Yeah, well, first of all, let me say I really enjoyed your talk. You know, a lot of lectures, a lot of talks focus on doom and gloom sometimes, and what I found really refreshing was a conversation focused on solutions. So that was really nice to hear. The first question that I'll ask is about the net zero water revolution. They say it's very interesting. How do we make sure that the water is going to actually be fit for use? Because treatment technologies are not always 100% reliable, even when supervised by trained operators and engineers.
Yeah, I mean, I think this is one of the big technological challenge of net zero water. And so we anticipate that the first systems will try to reduce the risks by ensuring that the potable water supply is rainwater harvesting. So rainwater collection for potable use is an established technology. It's used widely in places like Australia and Brazil. And I think with the next generation of disinfection, for example, UV LEDs and other technologies, it becomes a pretty reliable approach for drinking water supply. And then the risk comes from the gray water, the water that's recycled for washing clothes and washing dishes and maybe even showering. And with like things like membrane bioreactors paired with UV treatment and other kinds of technologies, coupled with the revolution in the information technology area, I think we can create systems that have a very low failure rate. And I think the question is, what is an acceptable failure rate for systems like this, and how much do sensors and actuators make them more reliable? So I think almost more importantly than risk of public health is risk of failure, because when you have a net zero home, if it needs someone to come out and fix it, it's not going to be very cost effective. It has to be as reliable as having a gas heater in your home that gets serviced once every few years, not need someone to babysit it every week.
Yeah.
Thanks. Shall I take the next question, Nancy?
Sure.
So Natalia is asking whether you can imagine a water 5.0 revolution if you link the adaptation of water resource management to climate change.
Yeah, I mean, I think what I'm talking about here, and I had this struggle with, like, as I'm writing this new book, I call it Water 5.0, and I'm like, well, we haven't really realized Water 4.0. So I still think it all fits into this paradigm of a fourth revolution. It's just going to be many different flavors. And I think the connection to climate change is that climate change is going to emerge as one of the big drivers of change, especially not like maybe now we see hints of climate change, but when you look at the climate change projections 20 years from now, the climate in the Mediterranean, for example, is going to be like the climate in North Africa. And here in California, we're going to look a lot like Arizona and New Mexico. And so I think that the climate change part is more the driver, and the whole thing in my mind fits under the fourth revolution. And I think one of the big dichotomies in the fourth revolution is whether we can increase our reliance on distributed systems or independent autonomous systems, or whether we're stuck with the centralized supply and treatment and recycle model that seems to be more prevalent today.
Great, thanks. I'll jump in with the next one. Masha's asking about removing salt from lakes in a cost-effective ways, because she mentions Iran, I assume.
Oh, sure. Well, Iran, Kazakhstan, Southern California, they're all part of the same problem, especially of in terminal lakes where the water goes to evaporate, but also just any lakes in an arid climate. And so when I put up that picture of the Salton Sea, I think about it because if the Salton Sea is a wonderful place where birds migrate and where you have some very interesting ecosystems in a desert environment, but at the current rate, the buildup of salt is going to cause a collapse of the system eventually. So I think we need to think about salt machines that are going to extract salts from systems that have been damaged by agricultural runoff and other forms of pollution. And in order to make that economically feasible, they have to get a heck of a lot cheaper. So I don't know what the salt machine of the future looks like. That's why we're doing this work on the graphene oxide stock. That might not be the way that it eventually goes, but just saying to people, we need ways to remove salts that have reached too high a level, and it has to be super cheap in order to be effective. So the other competing approach for doing that, if you read about the Red Sea, Dead Sea project, where people are proposing actually using seawater to dilute waters that are too salty. Those kinds of big thinking of moving water over long distances could be part of the solution if we want to protect those ecosystems.
Thank you. I'm going to move to Sarah Finley's question, and she's wondering what your views are on the potential of aquifer storage and recovery.
Well, ASR, aquifer storage and recovery, is one of the most potent tools in our toolbox that combines the existing infrastructure and nature-based systems with some of the emerging technologies I talked about today. So if you look at places like Arizona or Central California, there's a lot of progress being made in taking excess water from the environment and recharging it and then using it during times of drought. I'm particularly excited about the possibility of flood managed aquifer recharge, where in places where your rain arrives in episodic events, you might have the possibility of intentionally flooding farmland to recharge aquifers. So I think that these technologies these approaches will be enabled by technology, whether that's better weather forecasting, whether that's better geophysics and understanding of infiltration, or even actively managing the infiltration areas like they're starting to do in Southern California with dry wells. You can imagine doing this at a larger scale in a rural area to get more water into the ground. So yes, I'm very excited about managed aquifer recharge, aquifer storage and recovery, because it's proven to be one of the most cost-effective ways to manage large amounts of water.
Great, thanks. Another question, and this one's from Nastra, and she's wondering about the plants that are used for the treatment of horizontal plants. I'm curious if how they're affected if they're right. Absorb too many contaminants or nutrients.
We've done a fair amount of work on the plants, and one of the first things we were concerned about is that we might be creating an attractive nuisance by concentrating contaminants in plants, and then the wildlife gets exposed to them. What we find that isn't the case. So the trace organic chemicals tend to be broken down by microbes associated with the roots of the plants and the rhizosphere. A few neutral trace organic compounds like carbamazepine manage to move into the plant, but the levels are quite low. In terms of nutrients, most of the nitrogen is removed by denitrification, and the phosphorus tends to move through these systems. It doesn't really concentrate very much. The plants have enough phosphorus, and so the plants are not really a problem. I think the big problem in my mind right now is that we don't have a good way of removing phosphorus in these systems. Fortunate in the Western US, where we tend to be nitrogen limited and not phosphorus limited, so it hasn't come up. But if you were trying to apply something like the horizontal levee in a different climate zone or a different geochemistry, you might have to find some better approach for managing dissolved phosphorus.
Great. Thank you very much. I think we're at the end of the session. We also should let Professor David Sedlak go because he has to teach in 5 minutes time. So Professor Sedlak, thank you so much for this wonderful talk. Very, very inspiring. If you would be with us in person, you would get a big round of applause. Thank you so much for being with us here today.